And here's our agenda for today. So we're going to look at the big ideas in topic 3, grades 4 through 6. We're not breaking out today. We're staying together. We're going to uncover some meanings of addition and subtraction. We're going to do some exploration there. And so we're going to look at models and strategies, building a flexible toolbox for sense making and calculations. And then we're going to have some time for some Q&A. All right, so these are the big ideas we're looking at. We are 2 topics in, are almost done, so great work, everyone, for all the hard work and effort that you've put into this long-range plan. Again, we're going to emphasize that the purpose of the long-range plan is to keep us on the same pathway, not necessarily that our pacing has to be the same. So we're timing this just in time, always earlier than where the bulk of people will be getting into topic 3, because we know we want you to have it when you get to it. It doesn't mean that you are exactly here when we say we are here. We know that our pacing, depending on our class and our transitions, are going to be different. And the big idea concept that we're going to tackle today is addition, subtraction, and of course decimals. And then Conrad's going to jump in for this.
I'll jump in here. Just to answer Emily's question, she asked if everyone's has a focus on decimals or if it's just the grade 6s. Because of the way the grade 6 content was kind of split across topics 1 and 3, they have kind of engaged in things a little bit differently. It was mostly due to the integer inclusion in topic 1. So grade 6s really limited their work in topic 1 to whole numbers, whereas grade 4 and 5 have already started to uncover some work with decimals, representing, ordering, and comparing. And all of those representations and all of that work and thinking around decimals is going to come in handy as students start to add and subtract with decimals. Grade 6s, this topic, are digging into decimals for the first time, as well as addition and subtraction with them. So it's a little bit of a different skew. Grade 6 teachers, you might actually want to check back on our recording from session number 1. And dig into some of the grade 4-5 stuff, because there is some decimal representation stuff from their breakout that might actually kind of apply to your topic 3. I'm just going to switch computers for a moment. I'll present. There we go. Can everyone see that? Perfect. So I'll just pop into the grade 4 year-long map here, and we'll jump into topic 3. So topic 3 in the long-range plans is based on the overall expectation B2 from the number strand. And focuses on students using knowledge of numbers and operations to solve mathematical problems encountered in everyday life. The topics intended to focus on addition and subtraction only, kind of adding in multiplication and division into the operations that students are using in problem solving in a later topic. So junior students will eventually be sifting through all 4 of these operations to determine which ones apply to these real life contexts. We're just starting in topic 3 to dig into when we are using addition, when we're using subtraction, and what those strategies might look like. We've also included an expectation from the financial literacy strand around estimating and calculating the cost of transactions involving multiple items priced in dollars and cents, and without using any sales tax yet. That'll be later in the year as well. Grade 4 also only deals with whole dollar amounts in this case, so there's no cents involved. It's also really important kind of for us to mention here that grade 5 and 6 will be adding and subtracting fractions later in the year for the first time. The challenges there don't tend to be related to the thinking around addition and subtraction operational concepts, but they tend to be related to the renaming and the reunitizing of fractions so that they can be added and subtracted. So that thinking actually doesn't tie in too much to this work that students will be doing in this topic, but that will be coming later in the year, and that is a part of the expectations that we had to kind of pull out. If I can switch tabs here. So over to the curriculum site. These new expectations are a pretty close match to the 2005 curriculum, with grade 4 dealing with whole numbers up to 10,000 and decimal amounts to tenths, grade 5 dealing with whole numbers up to 100,000 and decimal amounts to hundredths, and grade 6 dealing with decimal amounts to thousandth and kind of an unspecified whole number range. If you haven't had a chance to explore the new site yet in depth, it's pretty vast and it's not the kind of thing that you can really just read through. A good place to start and a good place to check back in with every topic is the teacher supports under these specific expectations. So if I scroll down to addition and subtraction, here is the grade 4 specific that we're dealing with. Under teacher supports, there's quite a bit of really concrete information. And some of these new specifics are pretty dense because they've been compacted down and worked to include a whole bunch of previous expectations into one. So these teacher supports can be really valuable to check out. The teacher support section here for specific B 2.4, it speaks to a brief explanation of different types of situations that you might run into that might involve addition and subtraction, as well as some suggested tools and strategies that we'll be getting into later in this session that students might use. And then at the bottom of this section, there's also a brief breakdown, if I scroll down here, of the concept of algorithms, as well as some information about kind of our most common standard algorithm that we use in North America to add and subtract, and a little bit of a visual around digging into what it means as well. And then back to our long-range plans here, one more section I wanted to highlight for this topic. Down, there are sample problems along with the math up suggestions. The more button will take you to a Google Doc that contains a bunch more simple problems, as well as the expectation cluster. So if you were looking to for a page to print off, that might be a very printable one. And scrolling down again in the building fluency section, we do mention some math up number talks that might work. Some number talks from Sherry Parrish's number talk books, and as well, the 5 and 6 topics mention some options from Fosno's fluency mini lessons as well. So before we move on, is there any questions about that brief run through of the topic or about navigating that curriculum site or the long range plan site? Okay, so moving into addition and subtraction. We can think about the learning of adding and subtracting and really any operation as being made up of really two main parts. The how, which is building that toolbox of estimation and calculation strategies that we apply depending on the numbers involved kind of flexibly. And then the other piece is the when, which is a really kind of conceptual understanding of what addition and subtraction really are and what sort of situations they actually arise in. What sort of problems can we solve using these two operations? And how do I know that as a student? How do I pull that apart? The interesting thing here is that these two big pieces of learning aren't vastly different from what students have been engaging with in primary up until they come to us in junior, especially with addition and subtraction. The difference now is that in the junior grades, we're really going deeper with the problem solving piece and that understanding of what addition and subtraction are, because we're going to be expanding that to include other operations, and we're going to expand it into working with multi-step problems that might include multiplying as well as adding. And we're also extending our strategies to work with these larger numbers and to work with decimals, and probably developing new strategies as the old ones kind of stop working. So we're monitoring these strategies that we've used for years to see which ones are falling apart before our eyes as the numbers get larger, and which ones don't extend into decimals and which ones maybe do, and maybe we need to change which one is our favorite in terms of junior students making choices around strategies. So the teacher supports in the curriculum mentioned these different situations and different problem types. So I thought we would unpack those together because it really will give us a sense of the breadth of what we want students to experience. We want them to see all of these different types of situations that can be solved by adding or subtracting. Before I get into it, just wanted to mention that we have created a little takeaway for each grade with a table and some sample prompts that would be appropriate for that grade level for each problem type. So we'll make sure we share that at the end in our resources. This first type of situation is the joining situations. And these are definitely the most common. Students should have had plenty of experience unpacking these by the time they get to the junior grades. These are situations where you start with an amount, you make a change by adding more, and then your result is a final larger amount. Again, the most basic and the one that students have seen the most often is the equation that ends with the blank after the equal sign. So we've got a starting point at $14.50. We've got our big change. It's that jump along a number line. And then our final result is the thing we're trying to figure out. Very linear, very straightforward, very common, and hopefully very familiar. Number lines do tend to be a really good model for students to visualize joining situations because that change has a really familiar form in that arrow jump forward, right? We can kind of see the change and we know that's why it's addition or subtraction. It has a jump. In some situations, that change actually is the unknown we're looking for. So we know where we started. We know what our final larger result was. We're trying to solve and calculate what we added or what our change was. And obviously the thinking there is a little bit more complex than taking two numbers and combining them. Separate situations is the next type. They tend to be grouped together with joining situations a lot as kind of action type problems because you'll notice it's very similar. Even the graphic is very similar. You start with an amount, which usually is a large amount, and then you make a change by taking something away or removing, and then your result is a smaller remaining amount or something that's left over. Again, number lines tend to be a really valuable visual. It gives that amount being taken away a familiar form in an arrow jump, this time to the left. And once again, that's the starting point, end point, or even the change could actually be the unknown that we're trying to solve for. So the idea that I know where we started, I know where I ended up, how might I solve for what was that change? What did I subtract? And that kind of thinking will really help connect the reciprocal nature of addition and subtraction, the idea that they are the inverse of each other and can be used to solve a lot of these situations interchangeably. You don't have to use one or the other. And then we get into these part whole situations. Now these tend to be a little less common. Students maybe haven't had as much experience with them. If you ask them what adding is or what subtracting is, they probably wouldn't come up with an example like this. They would think about a combining or joining situation or a separate. They can be a bit trickier to pull out of problems. Bar models can be a really great way to unpack these and to talk to them. Again, a bar model has a hole on top and parts underneath. It doesn't have to only have two parts. It can have as many as are involved in the situation. One thing to note is, and students get hung up on this a lot, they don't need to be proportionally represented. You don't need to have the larger piece look larger and the smaller part look smaller, or even be accurate proportion-wise, because a lot of times your unknown will be one of those parts. So if I knew how much smaller it was already, I probably would not need to run any operation to solve it, right? Maybe students can go back and revise the size of those parts if it really bothers them after the fact, but it's more about just representing the situation. So I know I have this 3.85 total. I have one part that's 1.68, and it combined with something else needs to be the same as the 3.85 total on top. And again, just like in the number line situation and in the other two problem types, you can have the unknown fall anywhere on the bar model. You might even have both of the parts be missing in a very open-ended prompt. We know how much our total is. How much might those two parts have been? And there's some extra thinking that has to go in there. There's some student explaining that might need to be a part of that, right? What made you think those two parts were vastly different sizes? What made you think that they should be sort of equal or even, right? Might even be a connection into division down the line where students start thinking about a fair share scenario, right? And our final type of problem are these comparing situations. In this case, we have a large set and a small set, and we're comparing them by thinking about the difference between them. And so it actually looks sort of like a bar model on its side because the proportions and the way that you compare these parts is really similar, but the way that they appear in the real world is quite different. I like thinking about these in terms of a double number line or a number line that has the parts represented kind of next to each other, because the key that we're aiming to get at is that comparison, is that difference between their values. So you can see, for example, in the readathon example, we've got Antoine collected $142.15. So that's our large set. It's been represented along the bottom. And Emma collected $109.56, which is our smaller set and represented along the top. By lining them up like that, we can see visually the missing unknown there. How much more did Antoine collect in pledges? The difference is the how much more. Again, we're not looking at keywords. We're not looking for pulling out small phrases in these situations. We're looking for kind of a really conceptual, deep understanding of how do you know that you could solve this situation with adding or subtracting. And I think representing a situation, not necessarily as part of your strategy, might be a big piece of that for students. Any questions about those types of problems before we jump into the next little bit here? Again, we've pulled together a grade by grade set of samples for you to access that you could use right away, hopefully. And we'll share those at the end. Perfect. So quick conversation about contexts. The reason contexts are so important in these types of problems is that it's the way that students are developing their recognition of whether it's adding or subtracting, the types of things that happen, the way the numbers interact, and they only really happen in certain contexts. The other piece is when we're looking at curriculum expectations, we have this range of numbers we're trying to hit in whole numbers, and we have this situation with decimals that we're also trying to find real world examples for. So I just pulled together a few example contexts that might work. Distances tend to work pretty well for finding some large numbers. Populations also tend to work pretty well for numbers in the 10,000s and 100,000s. And then when you're looking for decimals, we're looking for decimals involving tenths, hundredths, and thousandths across all three grades. So you've got heights might be a common one that you don't just want to measure to the nearest meter. Actual lengths of objects in centimeters or in meters as well. Mass is a common one in kilograms and grams. Computer data is an interesting one that tends to be measured to the nearest tenth. And then it gets kind of rounded up to another, or reunitized into a larger unit. Money is a great one for grade 5 and 6 because we're dealing with hundredths, and grade 6s aren't done with dealing with hundredths, even though they have thousandths involved. And time can be a good one. Grade 4s have to dig into elapsed time problems, and it has some interesting halves and 0.5s and 0.75s involved, dealing with that kind of 60 minutes as our main unit. One thing to mention actually while we're in context is this idea that we have these ranges, but we don't need to only be dealing with the very upper end of the range. So just because grade 5 students are expected to be able to handle numbers up to 100,000 doesn't mean they're only dealing with numbers that are in that very upper range. That would really limit the type of context that they would engage with, right? As you can see, it's not a very common size of number to be operating with and to be dealing with in real world contexts, right? So it would be normal to include the full range of numbers that they might be dealing with. Again, just in the same way, grade 5 and 6 need to deal with tenths, and grade 6 still needs to deal with hundredths when they're talking decimal addition and subtraction as well. And in the real world, as numbers get really large, we tend to reunitize them naturally. We don't tend to deal with them with all their zeros and extra digits. You don't see a lot of news articles with numbers in the millions written out. We tend to say 1.5 million or 2.3 billion. And it's important to kind of model that to students and say, you might not see these numbers too often. And so as we're talking about this meanings of addition and subtraction piece, a lot of times in junior, we have trouble getting to it. We have trouble unpacking it and uncovering it because students have strategies. This is not a new topic or a new concept for them in the junior grades. And they tend to want to kind of pull numbers out and operate on them, right? And get to the strategy work and get to kind of the number work. One way you might think about slowing down is integrating some think alouds in your math talks or even in your minds-ons before you get into problem solving for the day. Consolidation and discussions, because they happen after students have fully solved the problem, it can be rare that they kind of discuss the thinking that goes on when you're initially unpacking a problem, when you first engage with it and you're figuring out the situation and the context and what you might need to do. That kind of deep process can tend to be hidden away because by the time we talk about it and consolidate it and discuss it as a group, we've all moved into our strategy work and our number work, and that's what we want to talk about and share. So taking time to really highlight that thinking as a math community can kind of shed light on that process. And what we pay attention to really shows our students what's important to us. So if we're always only talking about the numbers and the accuracy of our calculations, then students are going to shy away from this mattering and this kind of thinking being important to their math learning. So I thought we could kind of walk through an example of one. One way you can set up a think aloud as a group is to kind of cover up the numbers that are in a problem. You've probably seen and heard of this strategy in primary reading. It's kind of a closed strategy where you cover up words so we're having to think around them and make predictions. And it kind of forces us as problem solvers to really, all we have is the context. All we have is the situation. We can't pull the numbers out and work with them. We can't puzzle it out based on the numbers. We're kind of forced into really thinking about this as a community. So take a minute in the chat, share your thoughts. How might you model what you notice about this problem with your students? Initially, you might get crickets, so you might have to be the one actually sharing your thinking, what you notice about it, what that tells you about the situation, making predictions about what might be under those blanks and what you might need to do, or what might you hope students would say if you were having this math talk as a group. Pop some ideas in the chat. Very cool. Some great thoughts in the chat. Lots of discussion around that unit of kilograms and what that might mean to students, what their prior experience and prior knowledge might be that they're bringing to the table. And again, we might get wrapped up in a conversation about that unit and then talk to that, right? Say, whoa, we talked all about what a kilogram is and what it measures, and it really hung us up. And as we move forward, let's reflect back and see, did I really need to have like a really full, complete understanding of that unit just to solve the problem, right? And maybe how could we get past getting hung up on that kilogram unit? How can we, maybe that's when we build an anchor chart of units so that they don't hang us up as we come across them in these situations. Emily mentioned noticing that there's three things, right? Noticing that there's parts and a whole, right? And then I can do something with those parts and the whole. Trying to figure out what's missing, what the unknown is. That's kind of my job as a problem solver. What's missing and what do I need to do, right? Jump to that last little partial question, right? What was the mass of the apples? Again, benchmarks around kilograms, very cool. So thinking about those parts and hoping as a teacher we would get to talking about, I noticed that there's a whole and there's a part and then we're finding a part, right? I might have some sort of a bar model ready, or I might sketch it up as we shared our thinking. I might say, before I even look at the numbers, I might jot down a quick bar model here. And actually, right away, I know the apples are the unknown. They're the question mark. I know I have some oranges, I have some apples, and I have a total amount of fruit. So once I have those numbers, I should be able to do something with them, right? But before I have them, I might even think, I'm trying to imagine what the numbers could be. I'm trying to fill in the blanks, right? So if I'm a student, I'm going whole numbers for sure, even though they might not make too much sense in kilograms. So I might say, so maybe we're dealing with like a nice even 10 kilograms of fruit. So maybe 4 of those are oranges. How many could be apples? So there's should be more apples than oranges, because that's almost like a fluent mental math instant calculation, right? And so because the numbers are so simple, I can really flesh out what my job is as a problem solver. The idea that I am trying to find the unknown. What am I adding to 4 to get it to 10? And then you might end it there. Depending on the length of this math talk, you might stop. You don't want to get yourself into a 30-minute group conversation scenario when you're trying to also get to some problem solving that day. But you might, maybe you come back to the next day and you unveil what the numbers actually are. And so those could be pretty scary decimal numbers to operate with, even in the junior grades, right? But all of a sudden they kind of make more sense to us now, right? They have a contextualized place in our understanding of the prompt because we unpacked it with them removed, right? I could easily just jot those down into the bar model now. My total is 3.85 kilograms. Oranges are 1.68 kilograms. So I know I'm trying to find this missing part now. Then I can apply an operation, right? Work some decimal number sense strategy here to kind of solve for that. And again, we've kind of demystified it, right? That there aren't students in the class who sit down and instantly know what to do, but there's a thinking process that goes into it. There's an unpacking and a figuring out that we do to contextualize a problem. Modeling the idea of representing it separate from calculating, I think could be really powerful in the junior grades, moving forward into other operations, but definitely in addition to subtraction where we feel somewhat familiar.
So there's a quick question about the terms minuend and subtrahend. I think it was potentially mentioned a couple slides ago.
Mm-hmm. So those are just super mathy terms. In addition, you just have these two parts that are both addends, right? They don't need their own names, and then you have a sum. In subtraction, they need their own names because it kind of moves in an order, similar to division when you get into the quotient language, right? And so subtrahend and minuend are the parts of subtraction. One you start with, one you remove, and then your difference is kind of your final answer. I don't know that I would need to dig into that language with students. the simple knowledge that there are two parts that need to be differentiated between is more important. But you might have some students who want that language. You might have a couple who are into it, right? Okay, and I think that brings us to, we're going to jump into some strategy talk. One more mention of the idea of keywords. There's been lots of research into it across all operations and across all problem solving, and it just doesn't have the legs that students need it to have. Looking for specific words kind of occupies their cognitive space and their capacities so that they're not able to picture the actual situation. And if they can picture the situation and represent it somehow, that's a much more conceptual understanding of what's going on than just looking for a word and kind of pulling it out. It also tends to fail a lot. There are, depending on the type of problem and the wording of the problem, and when you come across these situations in the real world, it doesn't really work. People don't word it so that the word more always means you're adding, unfortunately.
All right, we're going to jump into some strategies for adding and subtracting, the other piece of that puzzle. And we're going to kind of break it down into the estimation piece and the calculation piece. But before we do, we're going to talk about this analogy of a toolbox. So, you know, students need a toolbox with a variety of tools. And when you think about it, even, you know, when we dig up that analogy, and, you know, the variety of tools you have in your toolbox determine how much more you are able to do, how much more skills you're able to develop. And so having a rich toolbox strengthens many aspects of, you know, a student's development when we're thinking about strategies, models, and strategies. So they help with conceptualizing a situation. They help with creativity, flexibility, and fluency. They help with many aspects, including estimation as a key tool. And when you think about estimation, you know, it's making sense of the numbers and knowing what to use when and which tools fit. So all these sense-making tools that is in, you know, your students' toolbox build confidence. You know, they're building capacity to rely on their own thinking rather than potentially rules they've memorized or just have tried their best to remember. So that overall building these toolboxes just has many facets of benefits. So in the next slide, we look at the use of models. We talk about models and strategies a lot. Models are visual ways to make sense of an addition-subtraction situation. So, you know, sometimes models are our strategy for calculating, as you can see in this number line where we're adding these two values. That's pulled from actually some of the samples that we've put in. And other times, models are there to help us make sense of a situation to determine what steps we're going to choose, what tools we're going to pull out, what calculations strategies we're going to use. So it's important students need to explicitly experience and practice both types of models. If it's just too one-sided, they don't apply it to either side. They're missing some tools in their toolbox. That being said, we're going to look at some of the potential models, graphical representations you might have seen and students might see often. So here we see a few different ones represented. It's important that we build this routine and rhythm of using models in our math situations. And we do that by modeling it as teachers when we're engaging in whether we're doing number talk or some whole class consolidation. The more we're modeling, the more they're practicing modeling and being modeled too. So they're an important tool, not only for figuring out a situation, but also for proving and communicating thinking as well. it's important that we create this level of freedom to students to create their own and choose their own toolbox of models by not only giving them the option and the freedom, but also exposing them to lots of different types of models. So we've got some base 10 materials, open number lines, and diagrams. As students grow through junior grades, we are, developing that gradual release from those concrete things that they need to allowing them to draw and have the capacity to create their own models with it on a piece of paper. So talking to some of our DL teachers in the distance learning digital realm, this is where the use of, a piece of paper is still important. And it'd probably be the best for, when you're thinking about modeling or a situation in terms of a diagram or a number line or even adding and using some algorithms, it gets really sticky when you're trying to do it on a digital platform on the computer. So it's worthwhile to take some time right now to teach your students some strategies in uploading, sharing photos in Google Classroom, Google Docs. Both slides and docs have this really cool, neat feature, insert image camera, and they can share their paper representation in a digital platform that way. So that's kind of covering the idea of models and graphic representations being important as students go, and then the gradual growth and release from concrete to more student created diagrams of representations of situations. So we've talked about models in our toolbox. We're just gonna take a few minutes to kind of walk through some of those strategies that are gonna show up in the next slide for addition and subtraction. Is that a question? Oh, perfect. So we talked about how, models can be used as a strategy themselves, or models can be used to represent a situation. And we're going to parse that out and kind of separate from the models the specific strategy students might use to add or subtract. So the first strategy we're looking at when they're doing the work of calculating is splitting. All right, so what happens here is we're breaking down numbers to create some manageable addition steps. Is usually broken down by place value. It doesn't have to be. That's what usually happens. Now, this is a strategy they might be pulling up from grade 3 with them from the primary grades. It's effective, but when you get over 3 digits, it gets cumbersome, and you need a way to organize this place value breakdown of strategies. And this is where could be a precursor to working on some standard algorithm strategies. But it's important with this strategy that we recognize that it gets sticky and it gets messy when you're up in 4 digits, 5-digit numbers, or when you're dealing with accurate decimal numbers as well. Next strategy looking at is the adding on strategy for addition. This strategy basically is one addend is kept intact, and then we break down the other addend to friendlier numbers. In this case, it's shown by place value. It's 120 and 5. And then those steps are taken to add. So students intuitively would be exposed to this as you give them opportunities as a diagnostic to add. And the next one is compensation. So when we're looking at compensation, it involves adding more than is needed to make a friendly addend, and then removing what was added afterwards. This is particularly effective when the addend is close to a friendly number. In this case, we've added 400 instead of 390, and then we take the 10 away. This is a strategy they might actually do mentally on number talk. So a lot of these strategies are great to introduce actually in number talks as they do mental math to find friendly numbers and friendly connections. And on to the next strategy. we're switching from addition to subtraction. You'll notice some of those strategies can be used in both operations. So we have adding on here. And for adding on in subtraction, it starts with, we're going to start with the smaller quantity. It's almost, we're inverting the relationship. And we add on numbers until we'll have reached the larger quantity in friendly chunks. So in this case, we've added on 11. And then the reason 11 is chosen here is to get to a friendly number to add on the rest of the values with. We get to 200, and then we add on 300, and we get to 500, and then we add on 56, and then we've reached the larger quantity of 556. And now the difference would be the sum of all those jumps we've taken to show the difference on that number line. And then on to the next strategy in subtraction is this partial subtraction process is decomposing what is being subtracted, or just the subtrahend, I believe. Am I right? I don't know if I have the right one. Doesn't matter. Into friendly parts, and each part is then subtracted separately. So this usually ends up breaking down into place value naturally. So in the first example, 325 is decomposed into place value pieces of 320 and 5 and doing it in steps. In the second example, notice that we don't always have to use place value. So sometimes it's friendlier and it's smarter for some to use a different value. So in the second case, 254 is decomposed in 243 because 243 is a friendly number to take away or from 843. Subtract from them. So then we'll have a friendly difference because of those 43 values. And then we take away the remainder, which happens to be, in this case, 11. And the next strategy, just have a couple more, is this one's compensation. We've seen this in addition. Again, we see it in subtraction, and involves subtracting more than what is required and then adding back the extra amount. It's effective because the number being subtracted is close to a friendly number, I've noticed. So in this case, instead of 285, we subtract 300 because it's easier to subtract that big chunk of 300. And then we add on the extra 15 that we took away when we subtracted 300. So this is, again, a great one to introduce in a number string or a number talk so that it's engaging that mental math practice. And our last strategy for subtraction is one of my favorites, the constant difference. So in this case, we are referring to the idea that difference between two numbers does not change. So if I shuffle one number on my number line and shuffle the other number the same amount, whichever way, to get them to a friendly value, or one of them to a friendly value, then my difference will not change. So with that, in this case, we shifted our line 15, positive 15, or added 15 to both numbers so that we can have a friendly number of 200. I've noticed that, my smaller number, if I add 15 to it, it gets to 200. That's funnier for me to process. So doing that shuffles my bigger number to, it happens to be in this case another friendly number, but might not always. And then I can do the subtraction a bit easier when it's 660 minus 200 as opposed to 645 minus 185. So that's another strategy that we can use. So when we're thinking about all these different strategies we've been exposed to, we want to not make them procedural steps. They need to be something that students are making sense of. So I'm going to hammer that point over and over. So that's important to remember as we're engaging with these, that we have to do it in a meaningful way so it doesn't become, hey, here's the 5 steps to do a constant difference strategy. That's not what we want. All right, so we are going to jump into...
I'm going to jump in for just a moment because Emily had a question about calculators, and I think it actually fits really perfectly into the conversation right here. The idea of calculators in terms of where they fit in this process is really important to think about and talk to, right? What are they replacing in students' problem-solving process, and what are they kind of not replacing? I would say they're probably replacing a standardized algorithmic calculation. So if I didn't see a friendly strategy that maybe would be quicker than crunching the numbers by using a standard algorithm, that would be a great place to think about. A calculator makes perfect sense here, right? I need an exact answer because of the context I'm dealing with, right? I've already done all the thinking. I know I will need to add to solve this problem. I know which numbers I need to add, right? And thinking about it, just replacing that one little piece makes a lot of sense. And for students to kind of see it, that's where it fits, that can be really, really powerful. You definitely still want to be doing some estimation before you punch the numbers into a calculator. The same way you probably want to estimate before you do some standard algorithm addition, right? I want to have a sense of how big this number should be because there's lots of spots I could slip up by using the algorithm. There's lots of spots I could slip and push the wrong button on a calculator, right? So I have a sense of how big this number should be, and then using a calculator definitely makes sense. Emily was asking specifically about grade 6. I'd say that makes sense. And yeah, like kind of towards the end of your work, your focused work in addition in subtraction, right? Because we have some strategies, we're comfortable with them. Let's make sure we're also developing the other parts of the problem solving process, right? Yeah. Especially if those strategies are getting in the way of that.
Yes, absolutely. And I think when we're getting to the end of the next couple of slides, I touch on them, the mathematical process a bit, and where the calculation fits. So we'll talk. It might add a little bit to this topic. Awesome. So let's unpack the standard algorithm together, right? We're going to put up an image, and I'm going to ask you, what do you notice a student might have been thinking here? What do you notice a student might have been thinking when you see this? Just pop it in the chat or unmute and share with us. Thanks for sharing those. I see adding from left to right. Yeah. Different strategies, mix them up. Perhaps thinking of each digit as 1. Yes. So when we see a piece of the standard algorithm, in this case, we see some of those misconceptions that might be happening. And when you see that in particular, it might not be just an error, it might be like an actual misconception. And you can see that the student has not regrouped, right? They're writing 2-digit numbers where there should be just 1. So there's a misconception as to the place value of those digits and where they belong and how they're organized. Excellent. So we're going to do a couple more prompts here. What might a student be thinking here? So I'm seeing people identifying some issues in the regrouping and grabbing the wrong place value. So you see that 5 plus 7 is 12, but they put the 10s in the 1's place value and the 2. So this gets a little bit confusing when we're using a standard algorithm and they don't have a place to organize. Again, in this case, it could have been just an error when someone is rushing, could be. But again, the strategy, the tool is not doing them the favor of being able to organize things. So we've got one more picture, and we're just going to pop it up there and talk about some of the misconception there. We've got 325 minus 189. When you look at those pictures, it's like 300 minus about 200 should give you about 100, but right now they have 200, right? So what's going on? Well, you can see that they're subtracting the digits. Just doesn't matter the order of subtraction. 5 minus 9, the difference is 4. So we can see that as we're working with standard algorithm, that a number of misconceptions do come up. Again, what is happening here, and a lot of the commonality we see in these misconceptions, is that students are thinking of procedures and following just procedures as opposed to just thinking about them. And one of the big key steps in that is the ability to do some sense making, and estimating becomes a key part of that. So I think that's bullet 3 on those, talking about, when you're building a routine of estimating in your math program, sense making comes in with it. So students feel that they're in control of the situation. They're not at the mercy of an algorithm machine spitting out a number, and then they're just going to take that number and be like, hopefully I get that right. Nobody is taking the time to go, okay, does it make sense when I subtract something that's around 200 from something that's around 300? What's the difference? It should be about 100. Instead of having that, you have students that are kind of at the mercy of the steps of the procedure. So estimation can be a big part of that representing step at the start of an addition subtraction situation. It can be the continual guide where they go, does this make sense? Is something off? And then it's important to note that students need some flexibility in how they estimate and how that is represented and exposed to them, so that they can have that tool of estimation to say, hey, does this make sense? And you'll find that students become more confident because of that. So in the next slide, we can see that, there are many algorithms that are out there. And basically the idea of an algorithm is that, structure series of steps to make sure things are accurate and efficient. So as we wrap up this idea of calculating strategies, I want to emphasize this math has these processes or these stages. So in math, this is what happens in every mathematical situation. You pose a question, a situation. You're going to go from the real world of that situation, create some kind of a model. You're going to perform some calculations within that model. And then you're going to take that model and translate it back into the real world to see if the question that you've started with has been addressed. When you look at that entire process or cycle of mathematical reasoning, calculation is a small window in the middle. And in fact, in 2020, it is the most replaceable piece of that math process and math reasoning stages. So that emphasis, we're not saying we don't calculate, but the emphasis you put on calculation should match the entire process. And so making sense becomes a really important piece of that. All right, next slide. So we've been talking about decimals in grade 6, which was predominantly all focused on decimals for topic 3. And the decimals that show up in tenths and hundredths in grade 4 and 5. What are some thinking strategies that stay the same? We know that, the principles and properties, the commutative, associative, those things in whole numbers apply to decimals. We also know that the strategies we've just discussed actually apply both to decimals and to whole numbers. But what are some things that are going to need reworking or changing? So the modeling situations where decimals are involved will require some adjustment. For example, students might rename wholes. An example is, a rod can be a whole. Then what does the unit become. So to kind of look at how you might approach those changes in the decimal realm, let's take a closer look at a situation. So on the next slide, we're looking at 2.4 plus 3 decimal 0. So you can add decimals by renaming the whole. So 2 decimal 4 can be considered as 24 tenths, which again is connected to that whole, what Conrad mentioned about grade 6 is looking at representing decimals. It becomes important here because you're able to represent 2 wholes and 4 tenths as 24 tenths, or 2 decimal 4 as 24 tenths. And so 2 decimal 4 plus 3 decimal 0 can be renamed as 24 tenths plus 30 tenths. Now that becomes a 24 and 30 because we've changed the whole values, which will give us 54 tenths. And then since I know that 10 tenths is 1, I know that 50 tenths will be 5. And then 54 tenths will be 5 wholes and 4 tenths, which will give me 5 decimal 4. So allowing students to rename these values and operate and renaming back extends their whole number strategies to conceptually into decimals. So this extension strategy into decimals by renaming is built upon, it actually extends to grade 6 when students are now going to apply the strategy of multiplication with decimals too. So having this exposure in grade 4 or 5 builds that into grade 6 when they're doing other operations as well with that. So that being said, we have come to the point of our Q&A. So we're going to address, we had a question in our Slido that was, that asked, can we please have easier LRP, long range plans, more laid out like for the first 15 days for the rest of the topics? So a resource that's kind of detailed like that, when we looked at the first 2 weeks, first 15 days, needs to contain much more than what an LRP is designed for, because an LRP is designed to guide us through that path and not necessarily dictate the very specifics. So the purpose of that first 2 week document is very different from an LRP. However, to support teachers with planning, instruction, and assessment, WRDSP has made a big investment into Math Up, and I'm sure you guys are aware about that. So Math Up was selected because of the numerous supports it provides for teachers. It provides learning about math, a little mini PD from Marion Small in each topic. It provides a menu of connected learning tasks with clear assessment foci. It includes editable formats, Google Docs, and modified, and they're shared directly with students through Google Classroom D2L in print form. And it's kind of set up as a whole program. So we wanted to reiterate, really, if we're planning, that first 2 weeks is actually intended because of the situation we're in to give you kind of a leg up on the first 2 weeks of planning while you get classes situated. Planning with that much detail would not be responsive to our students, right? We don't know your students as a system. We're gonna have very, very different types of students in our classes from grade to grade, and so we're not as a system equipped to make those planning and pacing decisions for teachers and provide that step by step, day by day plan. So the sequencing of math learning would work for all the cohorts in the entire system. Just doesn't work to provide one thing for everyone. So I think everyone kind of understands that. But if you're feeling like, hey, we need support in putting these planning pieces together, it's important that you really check out Math Up. And maybe sometimes in the rush of things, we haven't checked out all the things that Math Up has to offer because it's quite extensive. So that being said, in the next slide, we've provided a resource here to support you navigating the Math Up resource. It's connected to one of the websites, and it's got an orientation video and how to get started. And of course, we're also willing to kind of coach you and walk along with you as you are navigating. How do I start with Math Up? What's my next step? How do I use this piece of Math Up? So we're more than happy to kind of come alongside of you with that in that journey, but we think MathUp might be the answer to that question. So that is the one slide of question we had, but we do want to give you a few minutes to open it up and for you to ask questions. So do that now.
And if anyone needs to go,
yes,
it is 5:05. So we'll open up the floor for any questions. We'll stick around for a bit if you have any questions for us that we can discuss and answer. But feel free, if you need to go, you can head on out. I will put up our final slide with the bit.ly there for the slide deck.